Well, here we are getting ready to sketch a graph of a rational function, and the sign table for a rational function will look a little different, and we'll need to be able to interpret it. So that's the reason we're doing this. We understand that we start out by trying to find intercepts, and so we would look for the y-intercept. And of course, the way we find the y-intercept is we know that we have a zero value for x when we have a y-intercept, and so we put our zero value in for x, and you see in this function we would get 0 over -1, which will just be 0. So y-intercept is the origin, and so that would tell us one thing when we're looking for an x-intercept. And we might have more than one, but certainly we know that 0, 0 is also an x-intercept, isn't it? Now, of course, the way we find x-intercepts is we let y be equal to 0, okay? And then we need to find x. And we've already discussed before that that would really boil down to us having the equation 0 equal 2x over x squared minus 1. And when we multiply both sides by the denominator, we'll end up with 0 is equal to 2x. And of course, the only solution to that is x equals 0. And so we do have only one x-intercept that we'd written previously. Then we need to find the critical numbers. See if we can do this all at once. We need to find the critical numbers. Oops. Of f and of f prime and f double prime. So now this is going to take a little bit more work, and that's because finding the derivatives here is going to be more work because we have a rational function. We have a fraction. So first, let's just consider f prime. Now, this being a fraction, we have to use a quotient rule. So we'll have x squared minus 1 times the derivative of the numerator. The derivative of x is just 2. And then we'll have minus the numerator, which is 2x, of course, times the derivative of the denominator, which is 2x. The derivative is 2x. And so then we have the denominator squared. And we need to simplify that. And let's see, in the numerator we'll have 2x squared minus 2 minus a 4x squared. And in the denominator, of course, we have x squared minus 1, and that's being squared. Now, in the numerator, we'll end up with negative 2x squared minus 2, and that's all divided by x squared minus 1 being squared. And I don't know that it's of any great value to us, but certainly we could factor that numerator. That is, we could factor out a negative 2, and we'd have negative 2 times x squared plus 1 divided by x squared minus 1, the quantity squared. Now, while I was doing this, something occurred to me that we should already know a little bit about rational functions. And we ought to know a little bit about where this thing has asymptotes. Okay, so we know that it should have a vertical asymptotes wherever the function is not defined. And see, in this case, the function is not defined when the denominator is 0, is it? And the denominator is 0 if x is either 1 or negative 1. Okay, yeah, well, that denominator would be 0. The function is not defined there at all, is it? And so we have vertical asymptotes, which are vertical lines at x equal -1 and an x equal positive 1. Remember, those are actually vertical lines. We're not just talking about numbers. Now, we also recognize that whenever, we'll just point this out, whenever let's take a look at this for a horizontal asymptote, because what a horizontal asymptote is about, so you have a horizontal asymptote, it's really the question of what happens on the ends of the graph, way out to the right and way out to the left. So horizontal asymptotes have to do with the limit as x approaches infinity of the function 2x over x squared minus 1. Now, we've seen limits like this early on, didn't we? And the technique that we would use would be to look at the highest power in the denominator and then multiply of x and multiply the numerator and denominator both by 1 over that highest power. So we would end up with, or say divide numerator denominator by that power. So we'd end up with 2x over x squared, and in the denominator we'd end up with an x squared over x squared minus a 1 over x squared. Well, when we look at that limit in the numerator, we would have 1 over x, wouldn't we? And in the denominator, we'd have 1 minus 1 over x squared. Well, as x goes to infinity, 1 over x goes to 0, and downstairs would have 1 minus 0, because as x goes to infinity, nothing's happening to 1, but 1 over x squared goes to 0, and so we'd find out this limit was 0. And so we actually have a horizontal asymptote, okay? The horizontal asymptote of y equals 0. And we may have done that from the methods we used in college algebra previously, but there we now understand what all of our asymptotes look like. Okay, let's go back to finding these critical numbers. I apologize that I took a detour there. Let's look at this first derivative again. Now, we want to know what causes that to be either 0 or undefined. And the only way a fraction can be 0 is if its numerator is 0. And no matter what we put in for x squared plus 1 is going to be 1 or bigger, isn't it? It's going to be a positive number. So there's no values that make it equal to 0. But of course, there's two places where it's undefined. And that would be x either plus or minus 1, because that would cause the denominator to be 0, wouldn't it? Now, of course, those are not in the domain of the function, because the original function's undefined there as well. But we can certainly have a change in whether the function is increasing or decreasing, but we clearly can't have a place where we have a relative maximum or a minimum. I mean, that's just because the function is not defined there. So these critical numbers aren't going to give us maximums or minimums, but they may give us a place where the function changes from increasing to decreasing or vice versa. May. Okay, now let's next look at the second derivative, because we need to know the critical numbers for it. And so that means that we have to take the derivative of the first derivative. Oh my goodness, this is going to be a bear, isn't it? So what I'm going to do is I'm going to look at this first derivative form so that I can take its derivative. It'll be a little easier than that final form that I had below. So what do? We take the denominator, which is x squared minus 1 squared, and we multiply that with the derivative of the numerator. Well, in this case, the derivative of the numerator is negative 4x. And then we subtract, and we take the numerator, which is negative 2x squared minus 2, and we multiply it with the derivative of the denominator. Now that's going to be kind of complicated because we have to use the chain rule. So we'll have the exponent 2 times x squared minus 1 times the derivative of the inside, which will be 2x. Oh my goodness. And all that's over the old denominator, which is x squared minus 1 squared, and it's that denominator squared. Well, what I'll do here is I'll spend a little bit of time trying to make this look better. That is, seeing if I can't do something with that numerator up above. And so I'm going to put this negative 4x factor in front. And then I'm looking at all of the things that I have over here on the right-hand side. And as before, I'm going to do several things. I'm going to factor out that negative 2. And I'm going to multiply with a positive 2 that's here and the 2x that's at the end. And so it's going to end up being a plus. You see if you agree with this. And I'm doing several steps at once. You might need to go to scratch paper to figure it all out. But I'm going to actually have a plus because I factored out a negative 2. And then I've got a 2 times a 2 times a 2x, which will be 8x. 8x. And it will be an x squared plus 1 because I factored out that negative 2 times an x squared minus 1. And then that's all over x squared minus 1 to the power 4 because I would multiply the exponent 2 with the exponent 2. And now I go to look to see whether I can simplify further in that numerator. And here's what I'm noticing. That I have a factor of 4x, and I could even say a factor of negative 4x that's common. So I have a negative 4x factor, and x squared minus 1 appears in both, so I have an x squared minus 1 factor that's common. And what I have left over then is an x squared minus 1 in this first position, and a minus 2x times x squared plus 1 in this second position. And that's all over x squared minus 1 to the power 4. And then I notice that x squared minus 1 is a factor in the numerator and a factor in the denominator. Okay, so I can cancel one of these x squared minus 1s with one of them down here, so it's going to leave a power of 3, isn't it? So I have a negative 4x and an x squared minus 1 to the power 3 in the denominator. Now, in these brackets, I can simplify that because I'll have an x squared minus 1, and then I'll have a, I made a mistake when I factored out a negative 4x. I don't have any x's here. Okay, that would have been, I would have had, the 8x would have turned into just a 2, wouldn't it, when I factored out a negative 4x. So I'll have minus 2x squared and a minus 2. So what's in these parentheses ends up being negative x squared minus 3. And then I can factor a little bit further just to make this in a better looking form, and I can factor that 4x. I can factor out a negative 1, so it would become a negative of negative 4x and an x squared plus 3 here over x squared minus 1 to the power of 3. Okay, so now I'm looking for where this is 0, and when x is 0, the numerator would be 0, and of course the denominator is 0 whenever I use a positive or a negative 1, so the whole function would, the whole second derivative would be undefined. So altogether I have a total of 3 critical numbers. I have negative 1, or kind of critical numbers. I have 0. Remember, 1 and negative 1 are really pseudo-critical numbers because the function itself is not defined. But I'm going to have a total of 4 intervals here, aren't I? I'm going to have negative infinity up to negative 1. And then I'm going to go from negative 1 to 0. and then I'm going to go to 0 to 1, and then I'm going to go from 1 to infinity. So let's get the sine table ready. That's going to be how many rows? 1, 2, 3, 4, 5, 6, 7. We're going to have 7 rows besides the header row. Okay, as you see, I've set up my table here, and it might be useful to write down what the derivatives are so that we can evaluate them and have that kind of in front of us. So let me write those down. Okay. Now, let's start off, excuse me, with recognizing that when x is 0, y is 0. We kind of found that out earlier, but we can fill that in by looking at the function on top, f of x equal 2x over x squared minus 1. We put a 0 in, and we get, of course, 0 divided by negative 1, so we get 0. Now, when x is negative 1, of course, if we tried to put that into the function f, we would actually get negative 1 over 0, and that's undefined. So this function is not even, the function itself is not even defined, is it? And we happen to also, while we're here, remember that the first derivative was undefined there as well as the second derivative. And so we have undefined all the way across there. So we can't have a relative maximum or a minimum or even an inflection point, can we? Because the function's not defined there. So, oh yes, remember that's where we had a vertical asymptote. Oh yeah, okay. That's what's going on. So the function is not defined there. We just need to recognize, though, that we needed that to create the intervals on either side because we may have a change in either increasing and decreasing or a change in concavity. Okay, and when we go down to where x is equal to 1, we have exactly the same situation. The original function is not defined. We found out that the first derivative was undefined. I'm kind of squeezed in there, isn't it? And also the second derivative was undefined. That was where we had the other vertical asymptote. Okay, now what about, what did we find out with the second derivative at x equals 0? Was that not a, as I recall, oh yes, that was in fact a place where the second derivative was 0, wasn't it? So that was a critical number of the second derivative. So we might have an inflection point there. Okay, we filled those in, and now we start testing. And so, for instance, we would look at the interval from negative infinity to negative 1 for the first derivative, and we would test a value in there like negative 10 or something. Okay, but what we're going to see, I believe, that the first derivative there is going to be negative. And in fact, stop and let me just kind of talk you through it. For the first derivative, so I'm looking right here, for the first derivative, we could test interval by interval, but I'm noticing that no matter what we put in for x on top, x squared plus 1 will be positive, and on bottom, as long as we don't put a 1 or a negative 1 in, x squared minus 1, well, it might be positive or negative, but when we square it, it will be positive. So on top, we're going to have a negative 2 times a positive divided by a positive, so it's going to be negative. So that first derivative happens to be negative every place that it's defined. So all of these boxes are going to be negative. Now, don't misunderstand that you may be more comfortable by just testing values, and that's all right. Now, when we go to look at the second derivative, well, it's a little more complicated because, for one thing, the denominator has a cube in it, and another, the numerator, has just a plain old x. And so when x is positive, that would be positive. When x is negative, we would be negative, and then the denominator causes other issues. So we have to test a little at a time here. Now, in this interval, I've gone out and tested a value and found out that I get a negative second derivative in this interval. And I've gone out and tested, now remember, and then I tested in the interval from -1 to 0, which is a little more complicated because I've got to pick a value like -1/2. But if I do, I'll find out that I have a negative in the numerator, and I also, in the denominator, I'll have a positive, I believe. Let's see, no, I'll have a negative. And so anyway, when I test this, I'll get a positive value for my second derivative. And then when I test between 0 and 1, I find out that I get a negative value for my derivative. I'm just testing something like 1/2. And I'm making those tests go. And then in the interval from 1 to infinity, I find out that my second derivative is positive. And so now I've got my sign table completed except for my conclusions. So when I look at the first row, I recognize that it's decreasing because the first derivative is negative. It's decreasing, and we're concave down. Now remember, if you're filling out a sign table in my math lab, for decreasing, you're going to need to put the sign like this, and then a comma, and then for concave down, you're going to put the intersection symbol like that, which will be available. Okay, well, there's really no conclusions at x = -1, but there would be no conclusions, nothing to say here, but we happen to remember that we do have a vertical asymptote there. So just as a reminder, I'm going to put that in. Okay, and then the next row, we see that we're decreasing. And concave up. And of course, again, the symbols we would use, because we're not, my math lab wouldn't recognize us typing in decreasing and concave up, we'd have to use that symbol, and for concave up, we would use the union symbol. By the way, if we're decreasing and concave down, that means we have this shape, doesn't it? And if we're decreasing and concave up, that means we have this shape. But remember, these two shapes aren't going to be able to be connected because we have a vertical asymptote in between them. Okay. And then we have potentially, in this next row, because we have a 0 value for the second derivative, we potentially have a inflection point. And we see that the second derivative does, in fact, change signs there, doesn't it? Okay. It does, in fact, change signs, and so we do have an inflection point. Now, we're asked to put in an IP if, I think it's actually lowercase that we should put in. I'll write it that way. An IP for inflection point if we have to fill that into a table. And now we're not going to be asked to fill in the point value, I don't believe. I can't recall that for sure. But in this case, it would actually be the 0.00, wouldn't it? And then the next row we fill in, we see that we're decreasing. This function is decreasing all the time, isn't it? That's kind of strange. It's decreasing, and we're concave down. So we put in this symbol for decreasing and concave down. We put in this symbol again. So if we're decreasing and concave down, we're back to this form, aren't we? Now remember, these two pieces are actually going to be put together because we have an inflection point in between. Okay? And then we have x = 1. Well, we're undefined there. We happen to remember that we have a vertical asymptote. Okay? And then finally, in the last interval, we're decreasing and concave up. And if we were putting this in symbols, we wouldn't write decreasing, we would put this symbol, and we wouldn't write concave up, we would put this symbol. Okay, decreasing and concave up, would mean that it looks like this. But remember, these two, the shape above and the shape below here aren't connected because we have a vertical asymptote in between these shapes. Okay, let's put these together for a graph now. So let me let's draw the coordinate axes. Okay, now let's look at our sine table. Now, a couple of things in addition to our sine table is, for one, we knew that we had an x-intercept and a y-intercept at the origin, so that points on the graph. And we also recall from early on that we had a vertical asymptote at x equal -1, so let's draw that in here. We also had a vertical asymptote at x equal +1, so let's draw that in here. Okay, and then we also had a horizontal asymptote at y equals 0, which is just really is the x-axis, isn't it? So I'm going to just draw right above the x-axis to keep that in mind. Okay. Now, the way we're going to continue with this one then is we're going to first think out in this interval from -infinity to -1. See, I'm thinking of this interval -infinity to -1, and I'm looking in my sine table, and I'm decreasing in concave down. Well, I've got these two asymptotes that I've got to worry about, and so I'm concluding then that that's what this is telling me, is that my graph looks like this. Because I couldn't have that graph above the x-axis, otherwise it would be crossing the x-axis, wouldn't it? And I only have one x-intercept, and that's at the origin. And I know, so that fits in with the asymptote, both asymptotes, so I see that that makes sense. It's decreasing concave down. Now the next thing is we're going to look at the interval at -1 to 0. Okay, it's not defined at x equal -1, well, that's where our asymptote is. But when we look above, that says that we're decreasing and concave up. And see, that fits with this situation. We're decreasing, so we have to start up here, but we're concave up, and so we have this little shape. Okay, so the graph looks like that here. And then I'm looking at the interval from 0 to 1, and oh, by the way, we have a point of inflection at where x is 0. So it's changing from concave up to concave down, and we continue to decrease. So from here we're going down, but we're concave down. So our graph looks like this. And then finally we're at the interval from 1 to infinity. Remember, we're not defined at x equal 1. That's where that vertical asymptote is. And there it tells us that we're decreasing in concave up. So that means that we have this shape, but we can't go across the x-axis, not because of the horizontal asymptote, but we don't have any other x-intercepts. And so if we're going to be decreasing in concave up, and we also have a horizontal asymptote, then that tells us that we have to have this shape. Okay, so we're decreasing concave up, and there's basically what the graph looks like. We put those pieces together. And it's important that we kind of pay attention to what this sine table is telling us, because we're going to be asked to interpret a sine table and be able to decide what type of graph comes from that sine table. Well, I think that's the end of my examples for sketching a graph. Good luck on your homework. Do well. I hope you do.